welcome in my very hot garage. Oh, I just got a message. We're in the pre-stream. I can check my messages. Where is it? Nope. I'll check them out first. This music is like really in my ear. Let's tone it down. Where's the number? There's the number. Something like that. Good evening all. How are you all doing? My mouse has a wire today. I haven't charged it in a while since I haven't been in my garage studio in a while. So the keyboard is wired up and the mouse is wired up. Everywhere is hot, dude. Yeah, I think currently in the garage it's 28 degrees. That's not great. But I've opened the window and I've opened the door and I've opened the large garage door. And so there's a little bit of wind. I'll also get bugs, but you know, that's how that goes. So let's see who's all here. Bass ZT says, good evening. Guten Abend, what? Wait, how's this working? If I scroll over his name, it turns into Guten Abend, everybody. And if I don't, it says good evening, everybody. Is that some kind of auto-translate Google chat thingy? What? And then Greg E says good evening all, and Sevag is here. Hello, guys. Draadstaal says first. Well, you were the first at 9 o'clock. That's true. Hit the like button. That's always appreciated. Good afternoon, everyone. Good evening. You mean my browser has lied to me? What? Oh, they're fighting for first place. Printing some open grid plates for underwear for cable management. Everyone else doing fun things too, says Nico Bill. Yeah, we're gonna work on the now I forgot my own acronym. The wall sensor plate, the WSP, I don't know, that project. No air conditioning here either. Well, in our home it's like 22 something, so that's great. But yeah, I don't have like cooling in the garage, it seems. So we'll fix that in the next house. Then I'll have some nice air conditioning in my working spaces, I think, because yeah, that'll also be like, this is a flat roof, so that's why it's so warm here. And in the new space, it'll be behind a pitched roof, but I'll be like on the first floor under that roof. So yeah, I'm gonna use some air conditioning. I wish I could send you some cool Canadian summer, says Jade Anderson. Okay, I was in Canada a few years back. But yeah. Okay, I'll be waving around a lot because of flies and stuff, but we'll have to deal with it. So, let's have a drink. Today we have, let's see if I can actually still do this. Oh yeah, we have some Fanta Zero Sugar Lemon. I like that. And no bug spray. I'm more allergic to the bug spray than to the bugs, so lemon lime. I guess lemon is a theme here, but yeah. Well, I'm gonna go with the with this one first. I hope you fix everything because have the next house. There is no next house. What do you mean? I don't quite follow. Is this set correctly? It is. It's just light outside. Okay. We'll have to wait until the sun goes down for correct lighting. Refreshing lemon lime. Exactly. Yeah, I like the lemon lime stuff. And it has to be zero because, well, I've been offline for a few weeks and I had some health issues. It's slowly starting to get better. I'm like bionically equipped again. so we can monitor my sugar levels in real time. Let's see what it is. I ate like an hour ago, so okay. Well, it's not too bad. So we can see my sugar levels. I went for a walk here, so went down a bit, and then I ate, but I ate fairly okay, as in carbohydrates and sugar, so it should go down a bit again. But yeah, we're working on getting that better, because it was getting worse. I think my body is handling it less well, and yeah, you know, getting older. That's how things go. Still baking pancakes in the kitchen, but the TV is turned on to it. Nice. Your background LEDs are a bit boring. What do you mean? What do you mean? They're like a nice. What happened to the chat? What? What is that? Hold on. Okay, there's no chat here. That's also wrong. Where's the chat? YouTube chat. There. Okay. And then... Okay, now it's looking normal. Oh, okay. Okay. No, I am diabetic. I have been for quite a few years. So, yeah. Technologica makes it suck a lot less to be sick and get old. I love 2026. That is for sure true. Because to you know, keep track of your sugar levels, before I had to like look like a drug addict with the amount of pricks I had to do in my fingers, and now I buy this. And granted, it's $100 for 14 days, so that's not cheap. But I can monitor my sugar all day long, and it's so much easier to keep track of things and when stuff happens and what you should do and shouldn't do, and yeah. You went with iced tea with a lot of ice. That sounds good. Yeah, the house is somewhat progressing. It's not going as fast as I'd like, but I finally found a W installer I like. So like for the heat pump, the underfloor heating, the normal water, the sewage, the drainage, house ventilation, that kind of stuff. Here we would call it a loodgieter or W installer. I already found an electrical installer who listened to my plans and was like, that sounds awesome. When are we going to do this? So that's good. And some other stuff design-wise has also been finalized, and we've submitted plans to the municipality and waiting on that. And yeah. Have you linked it to HA so a lamp blinks when you need more sugar or insulin? No. I don't take insulin yet. I tried to avoid that. So 2 weeks ago I started some new medicine for that, some pills. And that, the side effects of that I'm still dealing with. Not feeling too great for the past few weeks. But I'm hoping it'll help with the sugar, and the side effects should subside after a few weeks, being tired and issues with bowel movements and things like that. So yeah. So yeah, diabetes, I'm type 2, and I've been able to handle it with just, you know, a bit of exercise and watching my food and things like that for the past few years, but it's been getting progressively worse. So now we're trying with extra medication and see if that helps. Yeah, the electrician was really cool. Cool. Well, today we're going to continue working on this guy. Last time, I believe we left off having imported a buck converter configuration. Do you plan to make a video about the new WLED features? Maybe. I haven't been into making videos recently. I've been doing more live streams because I've been stuck on some hardware design stuff, which is taking way longer than I'd like it to. But that's also looking pretty good. I should receive new prototypes tomorrow or Monday. I hope today, then I could stream about it, but not happening. So that's been kind of sucking up all my time next to the health issues in the house and things like that. So I haven't been into videos that much. I do want to get back into videos like about the house and things like that. But I can't really do all the development stuff and the videos at the same time. It's just too much workload, and my brain doesn't work that way, I guess. So not so much right now, but maybe at some point. I'll actually showcase a feature I developed as a secret today. More. Well, okay, I should say AI developed it, but we'll see. We'll see. I'm hoping to get that integrated in some form or another into the official WLED, but we'll see. Yeah, it just knocked me over starting that medicine, but it's slowly getting better, I think. So yeah. Anyway, today we're going to continue this, and one of the first things we should do is what we do every stream, and that's see if there's an update for KiCad, because we're using KiCad 10, so, you know. Let me resize this so I have a bit of chat there. And can I now share my screen display? Yes. Okay, I'll make that a bit bigger because, you know. Okay. And do I now have a browser maybe? Let's see here. There we go. Okay. Maybe I should just make it full screen, I guess. I don't know. Wait, why doesn't it fit? That's odd. Oh, okay. That's why. Okay. Well, we don't really need to... Whoa, that's a bit much. Don't need to see that part. There. Alright. So I don't remember which version we're on. Let's see. Quite good. 10. Well, I know we're on 10, but where did it open? It opened right here. Good. We are on version 10.03. Okay, and version 10.04 is out. So let's download that. Come on. You can do it. My poor PC. Download Windows. I'm in Europe, so let's go to Switzerland. Okay. 6 weeks is the sweet spot for you. Okay, well, we'll see. Oh, they're doing a donation drive again. Cool. I generally donate like 100 or 200 bucks at least. And, oh, you get a t-shirt. I have this t-shirt already. This is 2025. Do they have a 2026 t-shirt? But yeah, I like to donate a few $100 to KiCad, and I generally donate a few thousand to WLED, and, you know. Okay, download done. Let's close this. My PC feels slow today. I'm just waiting to see where the window pops up. Oh, it's over there. Okay. There. Okay. Oh, FreeCAD. Yeah, I've tried using FreeCAD. It's just, I don't know. It's not my thing, I guess. Well, it's a bit slow, isn't it? Let's see what my CPU is doing. How are we doing, buddy? What are we doing? Well, this is like the streaming stuff, so... Video card's fine. Yeah, I don't know. I guess it's just slow. Okay, let's launch it. So, last time we left off, I believe... Loading... What? I've never seen this window. Okay. I believe we left off having designed the PoE circuit like this. So that should give us about 12 watt at 12 volts, so about 1 amp output at 12 volts. But we don't really need 12 volts. So I imported this guy. And this guy takes in that 12 volts because we're using the same symbol as here, right? And it has some input capacitance. We probably don't need all of those because we have the output capacitance right here, but that's fine. And I like to use a AP62300Z7 Z67, which is a adjustable converter, and we'll look it up. We'll take a quick look. Where do I have a browser? I should have a browser. No, not here. Hold on. That's okay. There, it's from Diodes, so it's actually not a Chinese manufacturer. And the reason for that is because I like using it because it has some built-in EMI mitigation features. Oh, iTestings is here. Hello. It's a very small, it's like a tiny little bugger, so it doesn't take up much board space at all, but it can still do 3 amps officially. We're gonna need nowhere near that, so that's fine. And it's 4.2 to 18 volts. Well, we have 12 volts input because of the 12 volt that's coming out of the PoE circuit, so that is perfect. Oh wait, did I actually hide myself? Is that good? Do I want to hide myself? I don't know. Maybe I want to do this. Wait, hold on. There. And then let me filter this. No. Oh, no gamma there. There. So now you can see me. Ooh. And you can still see what's behind me. So that's good. Yeah, so it takes easily takes the 12 volt in. It supposedly has 3 amps out. But as I said, this has some EMI mitigation. So it has a proprietary gate driver. It doesn't have spread spectrum, I think. Dradstal's not awake, but he's still here. But at least it has some, and I like the layout's pretty decent to, you know, lay it out so that it shouldn't radiate too much. Not much else to be said about that. We have 3 amps out. We have a reference for we don't have the T version, so we should use this voltage reference so we can calculate what we need, because we need to decide if we want to have this make 5 volt or 3.3 volt. I think we want to make it 5 volt, but we'll see. It is 750 kilohertz switching. That's pretty decent. EMI reduction. It has very efficient at low load. Now, we're not going to be in low load because we have the ESP32 and the Ethernet and stuff running from that, but that is fine. Since when is Quinder a ghost? Well, I want you to see the datasheet. So, what we need to do, we have the input in this basic schematic, it says input if you want either 5 volt or 3.3 volt. This is our exact scenario, 12 volt in with 3.3 volt or 5 volt out. We need a 3.3 microhenry inductor. Okay, I think I already selected that because I copied this over, right? So we already have an inductor, but we'll take a look at it in a minute. And we're going to be around like between the 100 milliamp and let's say 300 to 400 milliamp. And then you can see if we go to 5 volt, it's above 90% efficient. Or if we go to 3.3 volt, it's like well, around 90% efficient for like the range we needed. And if we need up to an amp, I don't know why, that's like 3 or 5 watts. You know, it just becomes more efficient. So that's pretty good. We need a BST capacitor, a 3.3 microhenry inductor. We have an optional very small capacitor here. We then have a resistor divider to measure the output voltage, so it can adjust the voltage. And then we have 2 times 22 UF capacitors, right? And this is for 5 volt. Now let's see if they also have more information. We don't need all this information really. Yeah, sure. Okay. Blah 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 blah. All great. Yes, very good. Oh, more graphs. That's what you get when you buy it from, or when you take a part from like a very big IC developer. You get all kinds of information. So that's pretty good. EMI friendly, synchronous. It's synchronous, so we don't need a diode, and again, it raises efficiency. And for the price per like 1,000 or 3,000 deer, these are 7 cents. So I think that's a very, very good price. The black on the datasheet would need. From my preview, it looks pretty good, but if I need to change something, I like also being able to see my hands, but you can tell me. So it does pulse, that's fine. For low loads, we don't need that. Okay, don't need that. So adjusting the undervolt, we don't need undervolt lockout. We also overcurrent, be sure. I was hoping they had the resistors we needed in here. Okay, some temperature stuff, fine, whatever. Setting the output voltage. Okay, here we go. So if we want 3.3 volt out, we want a 31K and a, R1. Okay, so the R2 is always a 10K. And we have this one. So either we want a 31.6 or a 52.3. I believe I currently have it configured for 3.3 volt. So I have a 31.6. So that's correct. Okay. Our inductor doesn't change. We need a 3.3 volt. We need at least 10 microfarads of input capacitance. Well, we have 2 of those and a small one for some high frequency filtering. And then we need 2 times 22 microfarad for output filtering. Well, we have those, and again, one high-speed one for high-frequency filtering. And C5 was the option, and C6 is... Oh, okay, I'll have to check this. Where is C5? You'd think they put the graph like where we need it. Nope. Come on. Did I pass it already? No. C5, okay. Where's C6? Oh, C6 is the bootstrap, okay. I probably have that one. So that's this one. So pass the inductor to the feedback. Oh, it's supposed to be in front of the inductor. What? Then maybe that's C5. Let me check. Yeah, okay. Yeah, here's our bootstrap. So BST is on the switch node. Did I do this wrong? No. BST is connected to SW using through this capacitor. Okay, so we have BSTs connected to SW. Okay, yeah, that's correct. And then we have this capacitor, and I selected a 47. So let's check the data sheet. Okay, let me go back here. Jesus. Okay, there. Yeah, C5, I have a 47, and this one should be 100 or 330. Okay, well, I have 100. So I believe this is all correct. So that's just following the datasheet design. The more difficult part with buck converters or any type of converter will be the layout on the PCB. That will be very important, how you lay it out. And I think they have some section about it here. We're using the SOT 563. Let's double check that. Yeah, SOT 563. And they suggest this layout. Now, what is most important about this layout is that, okay, let's see. Being on a phone with minimum luminosity is probably not optimum. People don't forget to like and subscribe. Okay. So we have the V in over here and we have V out over here, and you kind of and ground is like here in the middle on this pin. So you kind of want the capacitors to be arranged like this, so it can make a nice little loop like that. So yeah, you can make a nice layout. The switch node is kind of but you know, they route it through here, and we're not dealing with a lot of current, so that should be fine. But yeah, this will come back when we start doing the PCB layout. So this is why I selected this buck converter. It's 7 cents. It's from a reputable party. It's fairly efficient, like above 90% for our use case. Our use case is directly in their data sheets, so that's also always nice. Now we can look up a few more things. They suggest, let's see what kind of inductor they suggest. Inductor. Choose to be between 30 and 50% of maximum load of 3 amps. Yeah, if you're going to do 3 amps, I agree. But we're going to do like 1 amp max. So, sure. Peak current, blah, blah, blah. Stay between 1.2 and 4.7. But we're using 3.3. They don't have any recommendations, huh? Okay. So, I already made this circuit on a previous design. So, let's see what kind of inductor I chose. Because I chose one to minimize size while being fairly efficient. It's not the most efficient inductor because it has a fairly high resistance, but we're using this tiny little inductor here, which can do 2.6 amps of current or saturation at 2.7 amps. So let's see here. There. Oh, let's look up this type. Okay, so it's this one. No, it's not. Oh, that's the, okay, sorry. That's the size. Let's see, MBCA, MBCD. Yeah, I believe we're using this one. So here you can see again the expected resistance. So if you're doing a very high switching speed, the more resistance the inductor has, the more heat it will generate, and the more losses you'll have. So if you're doing like something that's battery operated, you really want to make sure to minimize the resistance in everything so that it doesn't waste power, because resistance can basically be seen as wasted power because it will be transferred into heat, right? The heating rating is 2.6 and the saturation is 2.7. As I said, we're only going to be using like an amp or so maximum, I think. So I believe selecting this 2.6 amp inductor is going to be fine. And, well, you know, it's like 3 cents. So, yeah, you know, that's very good for our BOM costs, right? Yeah, we're not done yet. I placed this part in my schematic, but then in the options I set it to exclude from board and do not populate. You can do either. So if you only do not populate, you have the footprint, but your pick and place file won't have the part in there. But if you also exclude it from the board, the footprint will also be gone. Now the reason for that is, if we look at the EN pin in the manual, let me go to the top, or in the data sheet. Normally you need to have a resistor on the EN pin to either turn it off or turn it on. In this case, it says enable input. EN is a digital input that turns the regulator on or off. Drive the EN high, so whatever, 3.3 volt or whatever, to turn on the regulator, and low to turn it off. Leave floating for automatic startup. And floating means having nothing connected. The EN has a precision threshold of 1.2 volt for programming the undervolt lockout. So you can program when you want that IC to shut down. So let's say we have our 12 volt coming in from the PUE circuit, but we want it to shut down if that ever sagged to 8 volt. I don't know. Then you could program the UVLO of this chip to basically shut down if it sensed 8 volt instead of 12 volt, right? So you can have this chip enable automatically once it senses power coming in. It doesn't need a dedicated enable or disable pin, but we can check what voltages the EN pin supports, right? So let's check that. VEN. Okay. VEN supports 0.3 to 8 volts. Okay. So I was thinking like, okay, we could maybe tie the EN pin of the converter to the output of the PUE circuit so that it would only turn on when the PUE circuit would become active. But we can't tie it directly because the EN pin only supports 8 volts and not 12 volts our PUE circuit is generating, so that would, you know, screw up the IC. In this case, I think the automatic bring up is fine. And I need to see if it has a certain feature. I can't search for EN, that's a bit too broad. If it has auto... basically, I think this IC already comes up gradually. It doesn't suddenly spring on, because that can sometimes present a problem. But let me check if I can find it in the datasheet. I can't. Sorry, I have a little bit of a headache, so I can't remember what the feature is called. Basically, here they say if you have EN, you see the graph jump from 0 to 1. You see the V out coming up gradually, right? So it gradually comes in and it gradually goes out. Same with the current. So I think it already has like a gradual bring up. But let's see if we can find that in the text. Pulse with modulation, blah blah blah. Pulse frequency modulation. Okay, enable. Yeah, okay, so it has a soft start phase, right? So once the EN logic high, it becomes active, enables all functions, and the device initiates a soft start phase. So it slowly ramps up the output instead of instantly hitting it like hitting the input really hard, right? Pull up current source connected to internal LDO. VCC guarantees that if EN is left floating, which we currently have, The device will start automatically. Device still automatically enables once the voltage reaches the EN logic level threshold. Okay. It has a built-in 2.5 millisecond soft start to prevent output voltages overshoot an inrush current. Okay, so it gradually ramps up over 2.5 millisecond instead of instantly turning on, which would then stress whatever's generating that power, or the rail that power is on. So it gradually brings it up. Okay, so I think the current way we have it, so without any EN linking, is fine. Once it senses the 12 volt from the PUE converter circuit, it'll gradually bring this one up, and then it'll generate our 3.3 volt. But now we need to decide, do we need 3.3 volt or do we need 5 volt most, right? If we make 5 volt, we can use an LDO to go to 3.3 volt, and I'm pretty sure we want to go that route. But we need to figure out what this board needs. So does this expect 3.3 volt directly, or does it make 3.3 volt by itself? So let's look at the datasheet for that one. Wave share. Oh, did it already? Yeah, that's good. I believe this is all the way at the end. No? Resources? Yeah. Okay, schematic. Now I already remember that it has a power section here. And it has VCC 5 volt. I can't zoom in more, sorry. But it has VCC 5 volt. And that makes the ESP 3v3, right? So there is a converter, I believe it's over here. There is a converter on here, so I believe it takes in 5 volt from the socket here. And then over here is a small buck converter. Oh, there's a 100 there. Oh no, it's over here, because we see it has a 4.7 microhenry. Oh, we don't see that. It has a 4.7 microhenry inductor, and over here we have a 4R7 inductor. So this has a circuit on there to make 3.3 volts. So I believe we need to feed this thing 5 volt. And that's also what their own board is doing. And then it'll make its own 3.3 volt for on there. Here we can see this is being fed. No, we can't see. This is being fed by that same ESP32 or ESP3. So let's see which all it feeds a lot of things. Okay, yeah. Other way. What? Okay. What? Yeah, see, okay, you see all these, yeah. This is all being fed by that ESP3v3. Okay. So let's see what they have on that socket. Okay, so here's the interface. I wish I could zoom in more, sorry. Okay, so they do have ESP3v3 on the pin header, and they have VCC 5 volt with an diode, okay, to prevent feedback, I guess. Here they have VCC 5 volt again and ESP3v3 again. Okay, so what I think we'll do, we will make 5 volt, which will then travel through our board up into the screen board. And that will make its own 3v3. That's fine, it can use its own 3v3. And then we'll also make 3v3 for whatever we need on that bottom board we're developing, but for ourselves. We won't feed it back to the other board. So we'll basically not use these outputs. And we'll make our own 3v3, because our sensor board, which we're going to link to that, is also going to need 3v3, and it needs a clean 3 volt because of the sensors that are on there. And if you feed that a slightly dirty power, it could influence the measurements, basically. They could become less accurate. Yeah, that's basically what I'm saying. I test things. We're going to make 5 volt. We're going to send that to the screen board, and then we're going to make our own 3.3 volt also for our sensors and our own equipment, right? Okay. So we need to adjust this, because currently this does 3.3 volt, but we don't want 3.3 volt. We're going to make a new symbol here, 5 volts. Oh. So we want 5 volt, but then we need to change this resistor. So let's take a look again in our file, and I need to scroll for that a bit. There. We currently have that 31.6. We need to change that to a 52.3. Okay. Edit. 52.3. There. Okay. And do we need to change anything else? No, this is the same. This is the same. This is the same. This is the same. Same. Okay. So by just changing that single resistor, we have changed this from 3.3 volt out to 5 volt out. Some regulator can do 2 voltage or more. Sure, but then it's probably 10 times as expensive. So I don't think that's a good idea. We'll have to see in practice if this inductor can indeed feed enough power for everything we need to do. I think so. I think it'll be like 40-45 degrees or something like that, which is perfectly fine. But if it turns out that we need more power, well, actually, I don't think, that can never happen. We have 12 volts, 1 amp maximum coming in on this side, right? So that's 12 watts. If we'd have 2 amps here, that'd be 10 watts, and you lose some in conversion. This inductor would probably still be fine. But we're not going to use 10 watts. We're going to use, I don't know, 2 watts, maybe 3. So, yeah, officially, I think it'll recommend a higher spec inverter or inductor. But that's if you really wanted like 15 watt outputs over here. But we don't. We don't need anywhere near that. Okay, so I hope that explains this little circuit here, even though I copied it in. Yeah. Let's see here. Okay, we have the VCC 5 volt from the top here. And I'm going to copy this symbol. And I'm just going to do this. So now we can see that it's making our 5 volt, which I'll use on the board itself. But it's also linked to VCC 5 volt, which is linked to our header that we did in the first or second episode. Right? And then this ESP3v3, we're just never going to connect. It's not a phone charger. It don't need so much power. No, exactly. I mean, it needs to be handled like the transients and the screen, and it'll handle a bit, but I don't believe we need anywhere near that much power. Okay. So I do think we do need 3.3 volt. So let's design a 3.3 volt LDO. We could design a switcher, just like the top board has. So they make a giant switcher here. These flies are so annoying, right? So they have this huge switcher circuit here. We could do that, but I think we're just going to use an LDO, which can do like 1 amp output or something. We might even do 2 LDOs, depending on how clean of a power we want, right? And generally an LDO will be cleaner than a switcher because it's not switching, basically. So I don't know. Let's search for a fun LDO. We want voltage linear. Yeah, that sounds good. Let's make these go away. Let's see if we have a fixed output one. Output voltage, we want 3.3 volts. Okay. We want to it in. Oh, okay, wait. There was only one in stock. That doesn't sound right. .3 volts. Okay, now there's about 3,000. That sounds better. Ah, okay. Once these flies get you, they're never going to leave you alone. So let's look for one that can do at least an amp output up to, I don't know, 3 amp output, I guess. Sure. I don't care about the operating voltage because we're going from 5 volt to 3.3 volts, so anything will suffice really. Okay, sure, let's apply that. I don't like using AMS 1117s. Those are kind of old. Yeah, LDOs are cleaner but less efficient. Yeah, but we're only going from 5 volt to 3.3 volt. If we'd be going from 12 volt to 3.3 volt, we could still use an LDO, but only for very low currents. But with 5 volt, that's fine. So we can see what's popular. So the AMS 1117s are popular, but yeah. You ended up with a 7x7x7 inductor? Wow. Okay, Rob Keen. I had something similar on my DRL board. I had to sacrifice my preferred little buck IC with integrated inductor because I had to drop the frequency as low as possible to save on heat. Yeah, you know, those are considerations to make. Oh wow, the AMS 117 is really popular. Really? Wow. They're not great. Here's a TI one. It's 10 cents. So I like using a SOT 89 footprint. So let's see if we can find some of that. Oh, now we're talking. Still stupid AMS stuff. I guess the AMS is really popular for this function, huh? Oh, here's a diodes one. It's also 10 cents. Oh, they don't have a lot in stock. Okay, maybe I selected something. Can we select PSSR? No. Okay, let's clear this. I guess it's because I selected the output voltage. Well, I don't know. At some point we might produce this boards and then I need a few hundred, but I at least want to be able to prototype it. Man, why am I seeing so many AMSs? I don't like the 117. Go away. Let me select a brand I use more often. Oh, they only have one? Oh. Do they have one? They only also have one. Oh, this is a really tiny one. What kind of power can that do? 1 amp, low IQ, high accuracy, fast transient, low dropout. Okay. You can do 1.8 to 5 in. Sure, low dropout. I can do 1 amp. Okay. Okay, sure. They have various sizes. This one was a... Oh, it's a small DFN. Okay. Oh, this is actually pretty interesting. 10 cents. Let's keep that in mind. Let's go a few pages up so we're past the stupid 117s. I wish you could filter like what you don't want to see, but I don't think you can. Yeah, it's pretty warm here too. So we have an HD semi. It's a bit big. Yeah, I don't like that package. There's a TI with 15,000 in stock. Okay. It's probably a Chinese datasheet. Yeah. 70 dB. Okay. We'll remember that one too. See, we don't need a giant honking thing like this, because I don't think we need that much current. TLV 767, yeah. That is indeed a good one. I'm just trying to see if I see more familiar stuff. This is also... Oh, it's a bit big. At least we're past the 117 parts. Now we're getting a bit more expensive though, but... Yeah, no, we only need like 1 amp or something like that. We don't need a lot. Let's move it back a bit. Because I'm sorted by price, right? So let's see if we can find something in the 5 to 10 cents category. That is a nice, you know, 117, 117, 118, okay. I like something with a bit of heatsink. We're doing 5 to 3.3 volt. That's why I selected fixed 3.3 volt. So, so we just made our circuit here. This makes our 12 volt from the PoE circuit. Then we have the 12 volt in here, and we're making 5 volt. And we just want an LDO to go to 3.3 volt. That's it. So I'm just browsing to see what's fun to look at. You know, it's a it's a bit big. Yeah, the reason the AMS is used so much because it's cheap, and it's used in a lot of example projects, but it's an old design, really old. It doesn't have great PSSR, it doesn't have great transients, especially the really old one need like giant capacitance. It's just, you know, it's not great. Oh, here we go. Oh, I don't like that package. Okay. That's better. We're back to the one we found here. Okay, let's take a look at this guy from TI. We can get it. They have 15,000 in stock, and we can get it for about 10 cents. So that is pretty good. It's a precision linear, blah blah blah. Okay. Wide input linear voltage regulator from 2.5 to 16, so that works. Up to 1 amp load, that works. 1% output accuracy, okay. Much lower IQ. IQ is basically the standby power when it's doing nothing. It's not really important in our case, but again, if you'd be designing for something battery operated or a sensor that would be off for 90% of the time or something like that, that can be important. It has pieces are greater than 70 at 1 kilohertz. Okay, so, okay, that's pretty good. No, because you don't need an LDO works very differently, but yeah, because you don't need an inductor and other kinds of stuff. This one says stable with 1 microfarad capacitor, so that looks like a very modern design. It's in a small form factor, so this is WSON 6 2x2. That's basically the same as this. Wait, where did it go? Oh, seemingly I closed this tab. Okay. Basically, this ETA is in a DFN, but DFN or WSON is basically it's almost the same thing. But that's fine. 70. Okay. Okay. Yeah, whatever package. We already looked at the package we want to have. Feedback pin, we don't need all that because we're using a fixed voltage version. Yeah, I don't really care. This does 16 volts. Okay, it has fairly decent heat sinking. But I also like this ETA one. Now I lost the listing for that, so I need to open it again. Hold on. Oh, we want 3.3 volts. Oh, they actually, okay. Yeah. Okay. So let's continue reading this data sheet from TI a little bit more. Yeah, okay, temperature stuff. We're really not going to ask a lot of it. Oh, okay. Yeah, so this is basically the filtering it does. Our V-in is going to be 5 volt though, because I don't know why they only list this low, but sure. So the PSSR is basically noise rejection, and the higher it is, the better. That's pretty good. What? They need... Oh, okay, they're simulating a lot of load, I guess, for inrush current. Sure. Okay. Consumes significantly less output enable, blah, blah, very good PSSR. Drop out voltage, fallback. Okay. Thermal shutdown. Oh wow, the input capacitor is not required for stability. Okay. Reverse current. No, we don't have reverse current. Okay, feed forward capacitor. Okay, well we're using a fixed version, so that's not doesn't apply. Junction temperature. Okay, so typical is input capacitor. We have an enable pin, don't really need that, sure. Output, we don't have feedback. We don't have this. Okay, so we just have an input and output capacitor and that's it. Sure. If load transients are expected, okay, sure. So we wanted 2.2 microfarad at least. Sure. That's a TI datasheet for you. Ground. Feedback. Oh, that's stupid. So input, output, okay. Oh, and this is ground. Okay, I lay this out differently, I think. Huh. Oh, fixed. Oh, there we go. Okay, yeah. This is what we want. So since we're using a fixed version, we don't have to deal with the feedback crap and all this stuff. We can just have input, output, enable, done. And then you can make it a lot more seamless, so that's good. Okay, let's take a look at the ETA one, because let's see, this one is 3,000 about 10 cents, and this one is 2,500 about 10 cents. Okay, but this is an Asian brand, and I manufacture stuff in Asia, so yeah, that's a bit. I like those. I've used them before, but we don't need anywhere near that kind of level of yeah. Let's take a look at this ETA one. It's a little bit less accurate, but I don't really mind that too much. Do they mention PSSR? So they mention a 1 UF ceramics, okay. We're in the DFN 8 1.2 by 1.6, so that's nice and small. No, it's just too expensive. we don't need an LDO of 37 cents if we can use one from 10 cents of 10 cents. Okay, so this has a less wide input range. So we'll be prototyping at various stages, and then I'll of course make them for myself because I want them. But if there's enough interest, I can do like a run of like 500. And if those sell like in a year or so, that you know, I can do that. That's okay. Output, sure. Okay, that's pretty good. Okay, so this does at 100 hertz, 68 and 52. Okay. Above 10 cents, it's too expensive. Well, for our purpose, yeah. We you know, we don't need to pay like 3 times as much to get an even smaller package. That's just not needed. If you're like very space constrained, that can be a solution. You know, pay 3 times as much, get half the size of the chip that has the same performance. Sure. But I think we have enough space for this tiny little LDO. I mean, this isn't big, right? This is really small. And even this TI one is a little bit bigger, I think. So let's see. That is, well, it says it probably. 2 by 2. And this one is 1.2 by 1.6. So this one's a little bit smaller. But not by much. Okay, so here they're using 10 to do the graphs. Sure. It's okay, Rob. So, okay, yeah, that's good. Typical performance, dropout voltage, ice and current. Noise sensitive equipment, extremely low power, high enable input, sure. Okay. Okay. Okay, sure. Stable from 1.1 to 10. Okay. We're going to use a fixed version, so we don't need any resistor dividers. Okay, and then we go into... Okay. So I like this one. I generally tend to go for Asian brands. But I think the TLV one in this case is a little bit better. And size difference doesn't matter too much. Yeah, it's a slightly better. No, it's actually a bit better. Because we have PSSR here for, let's see. I think they mentioned it somewhere. Can't search. Okay. Nope. I know they mentioned PSSR somewhere. Okay, well at 1 kilohertz it's at let's say 45-ish. And this one says that at 1 kilohertz it does 70. Oh, okay. And at 1 megahertz it does 46. And here it only does like 20 something. Okay, we're going with the TI. Did I do that correctly? Yes, so this is 1 kilohertz, this is 100, and this is a megahertz, yeah. Load doesn't seem to matter too much. Now, they didn't list node here, but this one seems a lot better. And I'm sure they have, like, the same graph somewhere. Can't search, okay. Let's try and find the same graph just for fun. Quiescent current, okay, sure. I have a... What's this? A G502X. I like those. I have a few of them. I'm just interested to see what the pieces are. Oh, here we go. So at 1 kilohertz, yeah, okay, at one amp output, it's low, but at like 300 or 500, which we'll be using it at, it is around 70. Oh, wait, this is via 1.8. We're not doing that. Via 3 with 4.8. What kind of weird number is that? Sure, whatever. We'll take it. We're at 65-ish. Ah, but they're using a... Okay, but we don't need that. Okay, sure. And at 1, it's 40. Yeah, okay. It's noticeably better, so it does better filtering, basically, so less noise is going to come through. Okay. Yeah, sure, but it all depends on how much power you're asking from it, right? But we'll use this guy. It's decently priced if you buy like enough of them, and TI I can generally get pretty easily. External sources are also well priced. Oh, this one isn't. Sure. Okay, let me go close some doors because more bugs are coming in. I don't like bugs in any way, shape, or form. Okay, last one. Hold on. There. Okay. So, I don't know. Let's get this implemented, right? We're going to use our KiCad import feature again. So let's save this. Let's go to our PCB. And the reason we do that is because we want to use this import GUI tool. Sorry for the size. We can paste the LCSC part number here and hit import. It gives us this annoying screen. But if we scroll back, we can see that it imported the symbol, it imported the 3D models and the footprint. So we don't have to design those ourselves, so that's good. So now we can close the PCB and place a new part. And I believe we called it Q import. There we go, Q import. And now we have our TLV 76733 blah blah blah. Good. Let's see if it has the details listed. It does. Okay, that we don't have to worry about that. Now, it's definitely a Chine. Oh yeah, it's called. Let's see, plugin blah. Hold on. Import GUI for KiCad. You have Hordeur and Horam all over the place. Yeah, well, I'm in the garage, so we don't have all that over here. Anyway, this is a Chinese symbol because the input is on the right. And I like my inputs to be on the left. So what I'm going to say is transform selection mirror horizontally. Aha. And now the input is on the left. Very good. Okay, we're going to take our 5 volt because that's going to be our input. Ah. Okay, let's give it a ground. Now I'm going to cheat a little bit. For some reason it has multiple ground pins, sure. But I'm just going to do like this. And I'm sure that is like absolutely against any PCB guideline, design rule, whatever. I'm going to do that anyway. EP is generally... okay, sorry, I'm making a tact. EP is generally the pad that is underneath the component. So let's take a look at that. Let's go home. So they don't even have it listed here. They have ground. EN is connected directly to EIN, or to IN. That's fine. We don't have this. And okay, so let's see about. See, they have this thermal pad here. We have the WSON package, I believe. Yeah, WSON 6. So this thermal pad is often depicted as EP. Do they have it listed here? No. Well, okay, thermal pad. Basically, exposed pad of the package. Connect this pad to ground or leave floating. We connect it to ground so that any heat that is made inside of the chip is basically sunk into the ground, which is generally a large plane, so the heat can spread and dissipate easier. Connect thermal pad, large area, ground plane for best thermal performance. That's exactly what I just said. So that is this EP over here. And we have our in, we have ground, ground, and out, and enable. Now they showed that we can just connect enable directly to in. So enable pin, driving the enable pin high enables the device, driving this pin low disables high, low, blah, blah, blah. As an internal pull-up and can be left floating to enable the device, or the pin can be connected to the input pin. Oh. Okay. So we don't need to connect that at all. And then we're going to give it an X. Generally though, so you could do this. Generally though, I am inclined to connect it anyway. So let's just do that. If we can't, if it like makes for ugly routing, we won't do it. But I think it'll be okay. So now we need some capacitance, but what capacitance do we need? Well, I can use a fly racket and stuff, but the door was open. So, I mean, we'd be killing a lot. Yeah, we don't need UV low. That's fine. So capacitance. Let's see. Input. Do they have an input? Okay, they need one, but I think we saw that we might want more. Input and output, although input is not required, blah, blah, blah. Okay, blah. Input ripple PSSR. Input recommended sources, blah, blah. May be necessary if large. Okay, okay. Do we have a recommendation? Feed forward. I don't care. There. In. Okay. Ah, this is the one. Okay. Transient response. A transient response is basically how well it's able to adjust by varying load demands, basically. And they say use a 2.2 UF or larger. Do they list what size not to use? So sometimes they'll say use at least this, but not more than that, because it can cause instability. Trying to find it. Table account for an effective. Okay. Okay, they don't really say not to use something. So let's see. We have 22 10 volts over here. Oh, we'll need to change this. Just making a note for myself. We changed our output of the buck converter from 3.3 volt to 5 volt. 22 microfarad 10 volt is fine for 3.3 volt because that's like 3 times the voltage, right? And just like you saw in the datasheet, they talk about derating and things like that. But now we're doing 5 volts, so the 10 volt capacitor is only double that. So we probably want to go to a bigger capacitor because of the derating, and probably a 16 or 25 volt. But we'll fix that in a minute. I don't think we have the capacitors here that we'd like to use, so I'm just going to steal this one. And this will become a, I don't know, 4.7, 16 volts, sure. The datasheet says that it's not needed on the fixed version. So here we have out, we're going to ground, we're going to ground, and I'm just going to use the same capacitor over here, because that's likely going to be fine. Actually, let's make this a bit tighter. Go away. We'll look up these capacitors real quick in a minute. Feedback SNS. I don't think we need to do anything here, and we can just leave that floating, but let's check it. Where are my pins? Okay. Feedback pin. Input control. This is pin set to use the output voltage. Do not float this for Okay, with external resistance, do not float this pin. Okay. For adjustable version devices only, but which one did we get? The DRVR? The DRV. Yeah, we don't have a feedback pin. SNS output sense pin. Connect the output sense pin to the out pin, or to remotely sense that the output voltage at load, connect SNS pin to load. Do not float. For fixed version devices only. Okay, so the SNS pin is basically to sense the output voltage, but without any sense resistors. So we should not do this. We should do this. Right, so SNS output sense pin instead of a feedback pin. It just senses the output. Oh, wait. Output sense pin. Pin to the out pin. Or remotely sense the voltage at the load. Connect to the SNS pin. Right. Okay, so they're saying you can connect it directly to out. But if you maybe have something that is a heavy load or does heavy transients, you can connect it near that IC, so past all kinds of PCB traces and stuff like that, so you can sense it near whatever is drawing that big amount of current, and then it'll regulate the IC or the output voltage based on the voltage it sees over there instead of directly on its output pin, right? So that way it could protect against transients and measure and adjust the voltage better than doing it directly after the IC itself, because there it might be 3.3 volt, but like 10 centimeters further away on your PCB, it might have sagged to like 3.2 volts where you really need it. And then if you connect the sense pin over there, it'll help adjust that voltage to keep it 3.3 volt. In our case, again, I don't think this is going to be too interesting. Well, I just explained why they don't pre-connect it. It's basically a feature that you can connect it to wherever your load is, so that you can have it adjust based on the voltage over there instead of right next at the chip. Okay. Yeah. Yeah, in our case, I don't think we have any big 3.3 volt loads. Oh, I need to add a symbol. But, yeah, you know, it's good to have. Okay, so now we have an additional. We have our 5 volt, which is also tied to VCC 5 volt, which is tied to our headers over here. And we have a 3.3 volt on our board. There is also the ESP 3.3 volt, which we looked at the waveshare schematics that they use on the on this board directly. But we'll just let them have their own 3.3 volt and not use that. And we'll make our own 3.3 volt. For like the 10 or 15 cents that this costs with capacitors, that is definitely the best move. So let's fix the capacitors, because 5 volt and 3.3 volt, let's see how much a 4.7 16 volt cost. Because I like to do BOM optimization, basically. So let's take a look what I do there. Let's go to here. Let's kill that. Okay. So I know I want about 4.7 UF, right? So let's filter for that. I want it to be in stock. But you can see we can choose all kinds of sizes. Okay. Let's make it more specific. I want X5R or X7R. Okay. We can still choose all kinds of sizes, because I haven't specified the voltage. And as I mentioned before, if we have a 5 volt circuit, we want at least 2 or 3 or at least 3 times the voltage if possible, right? So I already mentioned here that it's going to be a 16 volt. But let's see between these two voltages. Now we see that we get less packages, but we can still choose between 0402, 0603, or 0805. So what I try to do in BOM optimization is I look here, we can get an 0603 or an 0805. But you can see for the same capacitor, 4.7 microfarad, 10%, 25 volt, same over here, the 0603 will cost you 8 cents, while the 0805 will cost you 3 cents, right? So now it's a decision. What is more important? Again, board space, because then we get the 0603, or cost. If we have plenty of board space, we can just get the bigger version, which costs less than half, right? So let's sort this by pricing. And we can see that an 0805 here is it's like not even 1 cent. This one is this is 1 cent. And I generally just look in here and I see, okay, the 0603s are plenty available. We got 6,000 here, we got 18,000 here. These are X5Rs, but if you're set on having an X7R, we need to scroll down because those get more expensive. X5, 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 X5. Here's our first X7R, and that's again an 0805 for 2 cents. And the X5R and the X7R is how well it responds to temperature differences and the voltage derating and things like that. So from this, if I look at this, oh, you even have a 1206 here. But the X7R, which is the higher quality one, if we want that in 0603, oh, we have to keep scrolling. Oh, we can just, do it over here. Let's say we want an X7R in 0603. We only have 2 results, and they are 6 cents and 8 cents. And now let's say, okay, let's keep the 0603, but a X5R is fine too. Now we have 37 results, and we can see that we can easily get one for like a cent or something like that. Okay, so let's deselect X5R again. But now let's say, okay, an 0805 is fine. Now we get 551 results for X7R, so the better version. We're back to about 1 to 2 cents. Plenty of stock, or well, reasonable stock. And we can get our 16 volt X7R in 0805. So even selecting capacitors is a difficult journey. And I'm going to make it more difficult. Oh, I already selected 25 volt. Okay, yeah. Yeah, I tried to go X7R because, also lifespan and temperature and things like that. But unless it really costs a lot more, I go X5R. But in this case, we can get this CTC one. Yeah, and I think as long as we're going 0805, basically I try to determine what is the best size that I need. But I see some Muratas here for 2 cents and some Samsungs here for 2 cents. And yeah, I'm not too worried about that. Let's sort by availability. Oh, here. We have 24,000 available. For 12 cents. Haha. Yeah, no. For the engine bay, sure. Yeah. Yeah, but we're nowhere near those demands. X5R is fine too. Anyway, I'm gonna go for an 16 volts 0805 because we see that we then have a lot more options, and we can get X7R, or we can easily get an X5R for very cheap, right? For like I don't know, less than a cent. So we go back here, and we say nope, this needs to be 0805. And then for the output, we have 3.3 volt, but since these are only like a cent or less, we're just going to use the same one, because if we would change it to a different capacitor, which we're not going to use anywhere else on the board, the fee for loading a different one on the pick and place machine is going to be way more than we save by using a specific one-time value capacitor, right? So I'd rather use the same one, even though it's like half a microcent more expensive, than have to use a different one which we don't use anywhere else. But we need to do this again. For 12 volt, we already have our 10 UF 25 volts. Is that correct? Did we select these actually? Oh. Okay, let's do this again for 10. Because we want at least 25 volt there, so 10. 0805. Okay, yeah, okay. We got plenty of results. 5 cents. Okay. Would it be cheaper if we did this? 0805, 0805. No. Okay. Okay. So a 10. Oh, these are 16. Wait. We need 25. Okay, still no problem. 10 UF X5, 25 volt 0805s. So that's fine. We can get those 7 cents. Okay, can we get those cheaper? Let's add more voltages. What is the cheapest? An 0603? What? Why is that cheaper? Oh, okay, it's X5R, but 1210 is huge. Okay. And if I say X7, yeah, then you're stuck in the like several cents category. Okay, 9 cents, 1210. Wow. Okay, yeah, that's not needed at all. No. Okay. I think X5R is fine. And the cheapest X5R is actually 0603. With plenty of stock. This one too. Yeah, and pricing. I mean, it's all a trade-off, right? You can go for the best capacitors, but you'll be paying like an arm and a leg. This might seem like the boring stuff. I actually like doing this stuff because it can make the difference between a product being viable and sellable for a price that's decent and, you know, being way too expensive. Here we can actually see like this giant stock. We can actually change this to, well, we're dealing with 12 volts, so maybe 25 volt isn't correct. 1210 is huge. Ask Claude. We can. Fable is back. Okay, maybe we need to go higher, bigger. Not sure. Oh, okay. This is okay. So 10 UF at 35 volt. 0805 for X45. Okay. So we need to, yeah, we need to change these. Because 25 volts a bit low for, no, 12 volt. Because of the D rating, right? So we can get some, we only needed 10, we have 20, so even with D rating, etc., we'll have effective 10 at least. So that's all good. Let's see what we had over here. Oh, we didn't name any sizes. Okay, so let's copy these. Oh, wait, these are 22s. I still made them 25 volt. I don't actually want that. I want 35 volts. Yeah, this can be 50 volts. Yeah, 0201s is fine for like 3.3 volt or 1.2 volt circuits. Other than that, you know. Okay, and last we need to check here is we need 22 UFs at, well, at least at 16 volts. Because we're dealing with a 5 volt circuit. But we need to check how large they need to be for that. They might actually need to be larger than 0603. So let's check that. Clear. 22. We want 35 or 50, X5R or X7R. Apply. We can only find 16. Okay. And the cheapest is a 1210, 1210, 1206 for 5 volt. Yeah. Oh, wait, no, wait. We're 16. Okay, 16 to 25 volt there. Okay, that makes more sense. I was going to say, what? Why is there only so little? We can do 1206, 1210s. Let's see, this is fairly in stock. 6 cents. 1206. Okay, 81,000. 0805s. Okay. And they're 8 cents. That's fine. So, let's say this. We get them for 8 cents. And if we say this... Oh, we get them for 6 cents. Yeah, okay. That's okay. Then I think I'm going to go for these. Yeah, 170,000, 200,000. Sure. So we can do 22 UF 16 volts for the 5 volt circuit in 0805. And then this one is a 50 volt, so that's always fine. There. Later, Dave. Odessa. Okay, let me fix this a bit. I need to change my view. I'm missing something. Let's see. Display options. Full window crosshairs. Yes. So much better. Now I can see the line when everything is aligned, right? So I like that. Okay. Okay. So let me... Oh, wait. Where are we? What? Oh, here it is. No clue what happened there. So here we need 22s with 35 volt. While we're doing this, we can just do this too. 22s with... Oh, okay, clear. 35 to 50 volt. Apply. Yeah, those are going to be big. That's fine. So, sorted by cheapest, we're already looking at 12, 21... Oh. Is there something cheaper? Oh, it's because these are 1.0 UF. So the smaller capacitance you need, it's easier to get it in a smaller package with a higher voltage rating, right? And the 0.1 or microfarads or 100 nanofarads, those will use like scattered all over the board. So yeah, those will just use a lot. So they fit in a lot of places. But here you can see if we want 22 UF with 35 volt, 22, 35, we're looking at 1210s. So really large capacitors because of the capacitance and the voltage needed. Yeah, but I don't think they have anything cheaper. I mean, we haven't selected a size. We wanted 22. We could look at 10s. Let's see if they have anything in between. Let's see. Okay, we can look at 10s and 15s. Let's see. Oh, yeah. $15 is a bit of an oddball value. No one uses that. Okay. So let's take a look. Let's do some theoretical design here. It has two 22s, so that's 44 microhenries or microfarads, right? We can do 44 with two 22s or four 10s. Okay, we can see. Let's keep it 35 to 50 volts. A 10 UF 50 volt is 4 cents. Okay. Let's look at something with more stock. That's 9 cents. Okay. Is this sorted? Yeah. And we didn't select any size. Okay. Okay, so let's look at 9 cents. So we'd need 4 of those. So 4 times 9 cents is 36 cents for 4 times 10 UF. Okay, now let's go to 22 and let's see something that's somewhat in stock. Yeah, there's only one here for 12, but others are like 20. Right, so I think we should take 20. And you put them in parallel. So we just calculated 36. Or we can do 20 times 2, that's 40. But it's 2 components versus 4 components, right? So it kind of doesn't matter. That's basically what it comes down to. Yeah, good example here. Yeah, it kind of doesn't matter. It just doesn't get any cheaper. We can look at 33, and I don't think it gets any cheaper. $2 a piece. Yes, very good. No. Yeah, sometimes it can make a big difference, right? That doing some 6 times 10 is better than 2 times 33 or something like that. I mean, we can look even lower, but that's not going to make a lot of sense, right? Because this is the most used value. These are cheap, but we need 10 of those, and that doesn't make sense, right? So, yeah. I thought 10s would be cheaper. They're 50 volts, so their D rating is better. I think these went up in price a lot. Yeah, true, Rob. Yeah, I don't know. I think in this case it just doesn't matter too much, so we'll use the 22s. But those will probably have to be 12 10s. 12 cents, yeah. Higher than required is better, but not too high. You can also go too high. Right, so let's add the 1210 denominator here. There. Just curious how much 47 UF is. It is what it is. This is scaled by the datasheet and the example board, what they suggest that you need. And there's calculations that you can do, things like that. That's all in those datasheets we went through. So this is also based on the datasheet we looked at. Yeah. How much? 47. Oh, on LCSE, sure. Let's see. 47. It's going to be expensive as hell. $1. But yeah, okay, so the one value we haven't looked at is ESR, and that is basically, again, the resistance of that said capacitor. And a lower ESR is better. And in that sense, it's better to have 4 times 10 than 2 times 22, because the resistance of 4 times 10 will be lower than the resistance of 2 times 2. And it again depends on your switching speeds and all kinds of other crap when this is going to become important. If you're doing EMI CE testing, for instance, this is an important factor, because you need to dampen certain frequencies, and certain capacitors work good for certain frequencies in certain sizes and capacitances with certain ESRs. That is basically why you see me putting a 0.1 here, a 0.1 here, a 0.1 here. Likely these are less or non-effective and not really needed, don't do much, especially in regards of functionality. They probably don't matter. But in regards of passing frequency EMI, they become more important. Less so this one, but this one over here, very close to this IC, is very important. You can basically see it as in a 10 UF or a 20 UF is much slower than a 0.1 UF. So having a very fast capacitor nearby helps with the switching, which is also going very fast. That then goes through that very fast capacitor that's close by. And then you have the bigger bulk capacitors further away, because those, well, are basically slower, but also see a bit slower. Yeah, you kind of need to see it like a ripple in a pond. If you want to mitigate that ripple, if you have something that can do that very fast, very close by, you can do it much more effectively than, one that's very far away. But those are a lot much bigger, or it's a bit hard to explain. Yeah. It's fun and frustrating to work on the balancing act of it all. Yeah, for sure. I think it's fun and until you fail all tests. But yeah. No, in this case, they don't need equal copper. That's basically almost impossible. But you'll see that during the layout phase, that physical layout does matter, especially for buck converters like this. But stuff generally just needs to be closer or can be further away. That's basically it, right? Yeah. And like for this LDO, this is a very low noise component. This is a very high noise component. So this is why here I selected one that has known EMI properties or mitigating properties. So you have a chance, at least a chance of passing certification if you lay it out properly. Instead of using a very cheap one, this one's also cheap, but that doesn't have those things, and then having no chance whatsoever of passing certifications. But we'll talk and see more about that in the PCB layout phase, where this becomes much more important. So, okay. Right, we don't have an Ethernet socket yet, do we? EMI is the electromagnetic interference, so it's radiated noise, but in the spectrum between 30 and 1000 megahertz. Oh, I can show you, I think. Let me see. I had a recent failure. That's why it's in redesign. So let's look at a failed test and a passed test. Let me look at that first. Hold on. Yeah, okay, this is a decent example. So this is an example of an EMI radiation test. So radiated emission. You have conductive emission. That is the noise that travels outward from your board over the cables. And you have radiated emission. That is the noise that travels outward from your board into the surrounding space, basically. So this is a radiated emission test for a DigQuad ABE V4, which has since been redesigned, because although this kind of passed, so here you have like outliers, you see the margin -6, but you really need to stay below the red line, right? And here you can see that 1 is still under by 1 dB, so 1 decibel. These are under by more, or 1.585, but I mean, this isn't great. In theory, this could pass, maybe, if you know, paid the lab a bit extra or something like that. So this is horizontal, and then you have vertical. Vertical, this one's doing better. It's still not great because we have a big peak here, we have some peaks here and stuff like that. But it's -6, -9, and -11.56. So this vertically is a pass. Horizontally, in theory it passes, but not with a huge margin at all, or any margin really. So I didn't like this enough, so I redesigned that part of the board to do things differently. But yeah, so these are the kind of tests where I send them to a lab. I went there 1.5, 2 years ago, or made a video about it too, where they do this kind of testing, and I make sure that my boards can pass CE and stuff like that, right? It's an expensive endeavor, but I'm large enough scale that I want to do these things. Before I just couldn't because it was just too expensive. But yeah, I try to, make all of this work within the measures of the law. So yeah, so in theory this passed, but I deemed it not good enough, and so it went into a redesign. And let me see if I have an example of something that passed nicely. No, don't do that. Well, I can show you a few things. Let's see here. This is an AN Pentamini. Oh, you can see it right here. So this was vertical. Vertical is generally easiest. Well, this stays well below any margins here, so that's perfectly fine. And then we have horizontal. It's a bit closer, but still, we're the peak wise, we're still at least at -6 dB. So I deemed that fine, and this went into production. Let's see. Do we have something else here? Let me find something nice. Sure. Here we have a graph for the Dignex Basic, as I still call it too. This turned into the Dignex 2. Vertical, you can see we're really nicely and well behaved. The Dignex 2 has all kinds of dampening circuits and other mitigation stuff in there. So we're at -10 and -22. And then horizontal, which is the harder way, or the harder kind, mostly for me, we're very nicely behaved at -12 or something, 18, 19, yeah. So this is what a very good graph looks like, basically. But for the Dignex series, I paid a lot of attention to this design-wise to make this pass really nicely. Right? So yeah. Ask Maybe ask some other vendors if they can produce these graphs. I'm not going to say more than that. But yeah, maybe do. Maybe. And then, okay, I am going to say more than that. Produce these graphs with the actual product name on there for that product. Not 10, 15 names on there. They all passed. No. The results for the actual product. Ask them. They can't. They don't have them. They don't pass. Okay, right. Anyway. Yeah, no, most of my big competitors, they make giant... They basically rig a board to pass, certify that, take the paper, add 20 other boards that absolutely will not pass, and then say, look, we have CE certification. Here is our giant document with all these names on there. They were never tested. They just put the names on there because they had one board that passed. It's a big hoax. Anyway, I don't, I do my own thing and I don't like to participate in that. So I do actual testing per board. Sorry, let's read chat. We are building on this, welcome Yvio Jacob. We're using this little sensor panel with display, and we're building a custom board to join with that, with PUE and things like that. Asking about, I have stock LED fixture ceiling panel makes a high-pitched noise when frequency depending on off, or dimmed. That is not EMI. No, that's just bad. Well, it's tough design. PWM, especially at audible frequencies, needs a lot of mitigation to not make noise, and they don't always do that. It's tough to get it right. So, are you typically able to narrow down the specific sub-circuit that's causing the failure? It depends. It depends. Like with Ethernet, I know we have a 50 megahertz crystal, and that will radiate a lot if you don't dampen it. And so then you see like 200 megahertz, 250 megahertz, 300 megahertz, 350 megahertz, 400 megahertz, 450 megahertz. And then you know, like, okay, something with 50 hertz or 50 megahertz is resonating, and you need to dampen that circuit. In other cases, it's not always clear, and it might require a few tests to pin it down or see if you can dampen it or change components. So like this dig quad here, I've been working on these V4 boards for a while now, and this one functionality-wise works great, but I couldn't get it to pass with the IC I wanted to use and the type of circuit I wanted to use. So this one has now been redesigned or tested twice, and I can't get it to pass. Or okay, I can get it to pass, but not in the way I like. I'm a bit high demand, I guess. So I've redesigned it with a new type of IC and different circuit, which will be coming in on tomorrow or Monday. Then I will test it, and then it'll go to the lab, and hopefully that finally solves that issue. And then I can bring out the V4, which has a lot of other changes and improvements and stuff like that. So now I don't test EMI myself. Maybe in the new house I can dedicate a room to that and do some in-house testing before it goes out. But it's very hard to do that in-house, basically. So I have a two Panasonic S5 IIs, which go to a Blackmagic 4 quad HDMI capture card. So I do everything in 4K 60. So this guy's 4K 60, that guy's 4K 60. I also have an S5, which I had before this, but I switched to the S5 II because of the better autofocus and things like that. So they're connected with HDMI. This one's using an optical HDMI. That's one using a normal HDMI. Into a quad HDMI capture card. That one has a 24mm prime. I had to read on the lens over here. So it has a 24mm prime, It's a 1.8, but I've generally set it to 2.5-ish aperture. This one is a pretty special one. This is a 24 to 105, but it has f4 over the whole range. So what that does is, normally if you have a zoom lens and you zoom out or you zoom fully in, it can't keep the same aperture, right? It might be 3.5 fully open, but then 7 when fully zoomed in. But that would mean I had to, everything is on fixed settings for everything. And if my aperture would keep changing, well, I would have to keep changing my settings. So yeah, this makes it so that I don't have to change any setting at any time, no matter the zoom level I use for my desk. Does that explain what you were asking, Josh? So yeah, everything 4K 60, 10-bit, into OBS. That's also how I record my videos, by the way. I rarely do anything on an SD card. I have a dedicated microphone, etc., etc. Such a waste of a good lens? What do you mean? Thanks, Josh. Yeah, I spent some time optimizing everything, getting good frame or good noise ratios, and lighting helps a lot. I mean, this now, of course, this looks all wrong. Oh, okay, the sun went down. That's the problem. So for this, I just changed the ISO on the camera, and then, that's enough to make me not hidden in the background anymore. So the top one is on ISO 6400. Sometimes it's on 5600. That one, I don't know, whatever looks correct with the current lighting, right? And I like the 60 FPS. Sure, Foxionaire, it's not a cheap setup. One of these cameras is like $2,000, and then a prime lens is like $500 to $800. That lens is like $1,500, and then you need a good capture card. I like the quad HDMI. That's like, I don't know, $500. And then I have this giant PC here. We can see the task manager here. It's a 5900X. It's a bit older now. 12 core. That's doing fine with recording in 4K and streaming in 1440p, because YouTube doesn't allow me to stream in 4K 60. And I recently upgraded to a 5070 Ti because the Ti has dual video encoders. So I can do multiple streams through hardware without a problem. And I record in AV1, and I also stream to YouTube in AV1. The YouTube stream is 32 megabits, constant, and the recording is variable depending on my screen content. So yeah, I like camera gear, but I also use this gear to make photos of my products, right? And do my videos and all kinds of stuff. So over the years, it's become better. Why NVIDIA and not AMD? If you want to do anything video streaming related, you want hardware encoding, and AMD hardware encoding is utter shit. Do you need more? Do you need more? In the most recent cards in RDNA 5, I believe it's become a little bit better, the engine at least, but the hardware, so the hardware is better now, but the software is still shit. So, yeah, no, don't even bother. Oh, you can see my stream going out here. Yeah, it's about 32 megabits average. Yeah, so I actually also fixed, we're going way off topic here. I'm now running this. Okay, hold on, let me close this. So the thermal camera and all the overlays and stuff like that should be fixed now too. Because I'm running Process Lasso Pro, and I have some CPU affinity set, for certain applications, I'm now pinning to certain cores. So thermo tools and a easy DMM and load application and OBS and whatever. So OBS I'm pinning to cores 0 to 11, so that if you look at a 5900X, right, we have lots of cores, but that's where you can see all this load over here. The 5900X basically has 2 CCDs, so I'm pinning OBS to 1 CCD, and then it gets all these cores to spread its load over, and that's doing fine. And then the other application, this one gets 2 cores, or 2 virtual cores, right? This one gets 2 cores, this one gets 2 cores, this one gets 2 cores, but they're all different cores. So now when I start those applications, they'll run on their own cores in their own core cluster on the CPU, so they don't influence OBS anymore and anything like that. So that's now arranged so that it does that automatically with Process Lasso. I bought the Pro version. It's pretty cheap. Yeah. And you can see it doing kinds of things here, like blah, blah, blah is affecting... Oh, Chrome is affecting system responsiveness. And I've made sure that it prioritizes OBS, so I get less stutters and things like that. Yeah, but I mainly got it for the CPU affinity, so that I can just pin it to a core automatically, right? And that's been working great. Hey, it's an unexpected maker. Yeah, so that I can run all these overlay tools at the same time now. They get pinned to a core, and even if they max out that core, I don't care, because it's running on a different CPU complex as OBS and whatever. It's basically isolated. So, yeah, that's fine. Yeah, that's how I fixed the stupid, my Chinese software is making my stream stutter issues. I basically isolated it into its own core, and now it's like, oh, too bad. Okay. Anyway, this was so off topic, but yeah, now it's well behaved and we haven't had any stutters. Oh, I've missed 2 frames. Aw, why did I miss 2 frames? I don't know. But yeah, no rendering lag, no encoding lag, no drop frames. Moving to Linux, I tried that a few years ago for the streaming PC, but again, the video encoding drivers and things like that were just less, and OBS is more difficult with capturing applications and things like that, so I moved it back. As final... Oh, what? Oh, yeah, okay, I just answered that. Yeah. Anyway, you're here in time for the end, Unexpected Maker. We designed this PUE circuit in a previous stream. We don't have a socket yet, but we'll fix that at some point. And then we made this buck converter. I guess we should start making it pretty, huh? Let's do that. Buck converter. There. And then we made an LDO. Yeah, this is kind of still, well, I don't know. Well, we might tidy this up at some point. We'll see. PUE. So let's see. Oh. Let's put it all in a nice box so we can, you know, move it around easier and stuff like that. I don't remember what this is for. This is the default theme for 10. I don't think I changed anything there. I think I drew this for... What did I draw this for? It doesn't really do anything either. GPIO 4? Do we have a GPIO? Yeah, we do. I think I maybe did this to demonstrate it on the PCB layout. No. This is just, well, yeah, I have some transparency there, but these are just dark windows. Yeah, maybe for the relay. I don't remember. Then I would have added the LCSC number in there. So let's check that. Oh, okay. It comes back with a solid state relay. So, but did we use the right pinout for that? Yeah, KiCad import. Okay. Yeah. Okay. Yeah. Okay. Yeah. So this is the relay then, I guess. So this will be solid state relay 1. Sure. Cool. Okay. Okay. Let me fix that real quick. See if that is what's going on. So turned off my color correction. Does this look different? And yeah, and I like having a bit of transparency there. So yeah. So this one I copied over, and it has everything already in there. We also did the resistor sizing and things like that. So that is fine. This is all good. And this one we imported, so it has the manufacturer name TI blah blah blah, and the part number and the LCSC part number and stuff like that. So yeah, that's all in there. Now here we have GPIO 4, and I've been thinking offline about this. Yeah, okay, we actually have a decent amount of I/O. Huh. I was thinking of if we needed a I2C port expander or not. I wasn't sure about that. These flies and mosquitoes and everything are trying to eat me. How long have we been going? 2 hours and 16 minutes. Oh, okay. Yeah, so I was thinking if we needed a port expander. In the end, we might also want to do something with some LEDs. But I guess we can also use pins to PWM that. I just don't know yet. We haven't really done a pinout map yet. Right? So, let's do that real quick. And then we'll look at some secrets. And then, yeah, we'll figure it out later. So let's say we need 4 times button input. 2 times relay output. 2 times for I2C 1. 2 times for I2C 2. Let's say we need another. Let's say, how many pins do we want? I don't know. 4 times random sensor pin. So some kind of sensor that needs its own pins, right? So this is 4, 6, 8. 10, 14. Okay, and we probably forgot something, right? How many pins do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13. Oh, I already forgot something. I want to have some LEDs we can control. And I want 4 LEDs that can do RGBW. But I don't necessarily want them to PWM. And even if I did, I would need lots of pins. Or I could use digital. But with ESP Home, that's a lot harder to control, to change them individually if you wanted to. So yeah, if we wanted 4 LEDs to do RGBW, yeah, okay, that's 4 times 4 channel. Yeah, okay, but we're not going to do those individually. Those can be non-individually controlled. So then we get 4 channels. Oh, this is also TX and RX, yeah. Yeah, I have a IC I use for that. Let me import that circuit real quick. It's easier to connect. It's harder to certify, and it's just harder in software in ESP Home specifically to control. And I don't really need 4 individually controllable, I think. I just want like 4 or 5, because I have an idea in mind with that. Let me steal some part here. Hold on. Okay, I just stole a part from the Dignext 4. Let's see here. Okay, so this is a AW9520. Oh god. Okay, let me just remove all this. La 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 la. That's fine. That's fine. Okay. This is a 16-port I/O expander, which is dirt cheap. They have 37,000 in stock. It's like 20 cents, let's say, and it can do some really nice things. No, that's okay. Oh god, this is the English data sheet, or the Chinese data sheet. That's fine. Okay, you guys can't read the. Okay, hold on. No. Yes. I'm so used to reading Chinese data sheets that I basically just read through it. This one. Okay. So this is a multi-function LED driver and GPIO controller with I2C interface. So it can do multiple things for us. It has 16 IOs, so we have plenty of pins. And each IO can either be an LED driver or be in GPIO mode. And it can do 256 linear dimming, so 8-bit dimming in LED mode. So it's a linear LED driver in that sense. And any GPIO can be configured as an input or an output independently. It does interrupts, it has deglitching. It can do 3.3 volt or 5 volt. Basically, it can do a lot of stuff for us. It has 8-bit dimming. but you can set the linear LED driving current per pin 37 milliamps. Well, it's syncing, right? It doesn't supply, it syncs, but still. And it's available in a nice small package. And so if we wanted to do something with some LED channels on there, I think this could be a really nice IC for that. So we can do button inputs with it. We can do the relay outputs with it. We can drive some LEDs with it. Yeah. So yeah, you can do, let's see, this is for LEDs. This is for a keyboard input matrix, for instance. Blah, 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 blah. I thought it had more examples. This is, it has some boot states that you have to take into account. So generally I use it in push-pull mode. That's also one of the unique things. It can do push-pull and not only open drain. So like the most used I2C expanders, they're really crappy in my opinion in what they do or how they're configured. And this one can do open drain if you want it, but generally I want push-pull, so it can define a 0 or a 1 state by itself. It doesn't need to rely on how, you know, a restrictive IC basically. But it does depend on which address you give it, which standard function it has. Yeah. So yeah, it supposedly has an 8-bit driver. I haven't used it for LEDs yet, but you can set the maximum current per channel also. So if you can set the maximum current and you have 8-bit dimming, in theory you have much higher granularity in my opinion, but I haven't tested with that yet. Yeah, so this one doesn't do PWM. This one does linear driving. I also know what you're saying, Rob. I wish I could find some I2C IC that would do 20 kilohertz PWM dimming, but they basically don't exist. I've half started designing my own, but I haven't finished that in any way, shape, or form. But yeah, so this is a 4x4. Where does it say it? Yeah, QFN 4x4. The AW9523B. And the best thing is, it's dirt cheap. It's dirt cheap. And so far, the tests I've done with it, I haven't done LEDs yet, but for GPIO in and outputs, it's worked great. So, yeah. You do need to read the design guidelines really well and the examples they gave and things like that, but sure. And if you're going to sync like 16 channels of 30 milliamps, it'll get hot, and there's some things to take into account. But if you need a single chip which will do a few inputs, a few outputs, and a few LEDs, I'd like to give this one a try. What are you using? Let's see. Yeah, okay. I think I've used this one, or I've experimented with this one too. Yeah, and I think this is only in and output, right? Not, they're 5-volt IO tolerant. I'd have to check that. Okay, they're push-pull. Okay, that's nice. Yeah, it looks comparable. It just doesn't have the LED function, but I mean, okay. So yeah. I mean, it's a little bit more expensive, not that much. But I mean, Unexpected Maker, check it out. I think it's a very nice chip which does a lot of stuff right. But of course, I've only had one test board with it. I have another test board coming in this Monday, where I use it as a normal GPIO expander to get some more IOs. But so far, my experience with it has been fine. And if we look at our project, and we want a few inputs, a few outputs, and a few RGB channels, which then don't have to be PWM, that might be interesting. Yeah, I/O expanders have during COVID the price for I/O expanders exploded. But like the standard, what is that one called again that everyone uses? I find it very restrictive and limiting. I don't like that one. It can only do pulled high and then pull it low and blah blah blah. It can't do push pull and only open drain. And this one, from what I in my search found, can do all those things much easier and much cheaper. And it can do LED driving, so, you know. Yeah, it has all the controls and blah, blah, blah. It has good documentation, too. So, it has a software design guide, which I guess is more important for you. I let Claude handle this for me. Yeah, but they do have some good documentation here. Like, okay, if you want to have these in series or in parallel, and what you need to do with the address lines. You do need to read all the documentation, because there's some gotchas in there that aren't like the reset pin, and the reset pin basically needs a delay, which isn't in the datasheet but is in one of the other datasheets. I don't know. But I believe this circuit will work. We'll know Monday. I'll know Monday. But you basically need to delay the reset while it's coming up, otherwise it doesn't boot or something like that. I don't know. It's not too complicated, but yeah. Linear dimming. So yeah, we might want to use this IC in the future for this project, because it'll just save a lot of pins having to go. I mean, the P4 has a lot of pins, so I mean we have a lot of pins available, but for stupid things like button inputs, relay outputs, and some RGB dimming, maybe we just use that IC of 20 cents, and then we have plenty of pins left over for other stuff. No, it wasn't for a secret. No. It's just tied to the other board. So, okay, let's leave that in there for now, and yeah. So one of the things I wanted to show today. Let me prepare that a little bit. Yeah, we'll do two. I'm having fun. We'll do two. So let's get this mess of wires first. Where is it? Yeah. Okay. Go away. There. We'll take a look at this mess of wires first. This is a Dignex 2. And the Dignex 2 has always had a certain functionality which wasn't exposed yet. So this week Fable came back to Claude, my friend Claude, who I talk to a lot, and I asked him to design a certain circuit for me. Okay, and well, he did. Or sorry, I asked him to program something for me, and he did. Yeah, Yeah, I saved. Oh, the KiCad's still open. But I saved it. No worries, no worries. I saved it 100 times already. So here we have a dig next to. We have 2 LED strips. And the LED strips are connected to the data output. So we have data 1 and data 2, obviously. But this one on the left here is connected to this power output. And this one on the right here is connected to this power output. Okay, so I'm going to do it like this a little bit. I don't know. There. So let me open my router real quick because I need to know the IP. Ah! I'm being eaten alive! Okay, let's turn that on. Okay, so that boots normally as you'd expect. Okay, we get an IP. One moment, please. I mean, I don't mind the bugs, but I do mind them like flying in my face. Okay, I've got the interface. Let me get this. Let's do that. There. Right, so this works like you'd expect. We can do some effects and things like that. And everything is as it normally works. But what I and Claude, my friend Claude, have been working on is if I now hit the power button for segment 0, this strip turns off, but only this output now turns off, right? We're used to, if we disable all outputs, this doesn't have anything connected, so it dims a bit slower. Everything turns on, and if we enable all, everything turns on. But now, if we have segments for multiple different LED strips, we can now control the relay circuit that's on there for each output individually. So you can, potentially save even more power than if you'd only have generic everything off or everything on control. Because even if you had like 4 or 5 LED strips connected, if you had a bigger controller, even if just one channel would be on, all the channels would still be using power. But in this case, you can turn one of them off and it'll just turn off that specific channel. Now, how does this work? In the segment interface in WLED, I basically added a little part, and here you can select which of the outputs. So we have 5A1, 5A2, and 10A1. They're the same as are basically displayed on the controller itself. And you can just say, oh, my segment 0 is linked with 5A1 or with 5A1 and 10A1. And then that's it. That basically does it. It sounds so simple, except it didn't exist yet until a few days ago. No, I had the door open because it's 29 degrees in here. I'll be moving to the main house and there it's fine. No, this is software controlled, so it doesn't measure anything. Speaking of measurement, though... Oh, there we go. So let's see if our measurements are working. If I now turn off this channel. Yeah, and if I turn off this channel. Yeah, works. Okay, cool. So let's give it more power. Our power factor is horrible. Yeah, but it has MOSFET circuits in there to actually cut off the channel. Not yet, Foxtionary. I'm playing with this, and it's fully AI coded, so I'll have to talk to the WLED guys if they want to accept that or not. I can imagine they might not want to. But yeah, so the way it works more, you can configure more here. You can configure per segment which outputs are linked with that if you're doing power injection and stuff like that. There is a nice overview now in the info section. So we have like relay 0, that is the external relay for if you're switching on and off your power supply. That automatically switches off if all the segments are off, basically. We can see that relay 1 and relay 2 are connected to segment 0 if you're doing power injection, and relay 3 is connected to segment 1. And, well, this is just the most recent build from the GitHub. And if you look here in the user mods, I also made a lot of changes to the multi-relay. We can now name each relay, and I'll have this pre-configured in the firmware builds I provide. So this is named external relay, and this is named 5A1 and 10A1, and so it corresponds to what's actually on the case. And you can see which pins. You can add a delay per pin if you want to. And what I also added, what we just talked about, you have an expander selector here. Oh, this is the stupid one that everyone uses, the PCF8574. I really hate that thing. It's a stupid expander. But anyway, I don't like that expander. So I added support, or I asked Claude to add support for the AW9523. And if you do that, you can enter the expander address. You can configure it into push-pull mode, which you generally want, so it's auto-selected. And then you can also select. Oh, hold on. The pins on the expander, basically. I guess I need to save it first before I can select those pins, I think. Hold on. Let me check. Yeah, okay, so now we can select P0 to P1 as expander pins that we want to use for this relay or whatever, right? Oh, it's actually a change that needs to be happen. Why did it show me expander pins when no expander was selected? Bad. This is the original functionality. I didn't change that. I don't like that. We're going to change that. I don't need to see the expander pins if I don't have the expander selected, right? So yeah, so it should add support for that expander, untested. We'll be able to test this on Monday. And it adds naming and yeah, all kinds of other features to basically turn into this. Or air cookie. This is this multi-relay user mod is made by Blazoncheck. So I'll discuss it with him. So yeah. I did added WLED slightly to add this here, but if you don't have the multi-relay user mod installed, this part just doesn't show up. So I'll add that as a PR, and then we'll see. Yeah. Now, that it doesn't seem like a lot, but going forward, this is functionality which, in my opinion, is going to matter a lot, because can I turn? Yeah, can I turn this off? Okay. Pulled out too much. What the? Okay. Let me move this away. And move to some other crap that's still on my desk, which I was working with. Let's see here. This is all tangled up. Hold on. So yeah, I'm hoping to integrate this into the Quinn LED builds at least, but also PR it to WLED so that any board can make use of that. Now, of course, no other board has the hardware for that. They only have a single relay and then turn everything on and off. But yeah, that is not up to me. I need this part. Okay. Yeah, so here's another Dignex 2, and I'm using the QEXP port to feed a enable pin and a data pin to a diff power sender, and I'm using the USB output of the diff power sender because it takes 55 volt in but provides 5 volt out to the USB port of the Dignex 2 to power it. Yes. Okay, let's remove the power meter because that doesn't work for this. Oh, sorry you lost your uncle there, Greg. Don't worry, it didn't miss too much. Okay, so I'm powering this with 55 volts. Let's go. And what it has connected is a power diff or diff power receiver RGB CCT medium end. Don't worry about the name. It's a work in progress name, but it basically takes the power over the Ethernet in and the data signal and outputs it as an analog signal. But the thing I wanted to show you is that connected to that is this guy, which is a normal dig to analog plus. So you can have one diff power sender and receiver for specifically this receiver. There'll be multiple variants using the UTP cable and then the buck converter. Let me remove this. And then there is basically a dig to analog plus output on that board, so you can feed multiple other dig to analog pluses in series. So if you wanted to have multiple controllable lights, but you only wanted to run one cable from your central location, and these lights would be near a certain location where you wanted to have them, but you do want them individually controllable, but they are analog, like a group of downlights or something like that, you can use a single buck converter and then power all of these boards from that single board connection, basically. That's kind of what I wanted to show. And I'm not sure if I've shown the analog dimming board before. Hey there, Pepsi. Deer issue. Oh, okay. I hope all is well with the deer. So yeah, that's just changed or added functionality where you can have a single analog receiver and then daisy chain multiple off of that, so you don't have to run a diff power port for all of them. You can if you want to, or if you need like more than 100 watts. But if like one lamp or one group of lamps only needs 20 watts, and then you have another one nearby, you can run some normal 3-wire cable that needs another 20 watts and then maybe another one. You can do all of that with a single board and some dig to analog pluses connected to that. And then those are individually controllable, but still use the power from a single buck converter, blah, blah, blah. Let me look up the IP real quick because I want to show one thing. 131. Now, why is the power option that I just showed you important? If I turn if I turn the power off and the enable pin goes low, it turns the power off to the remote board, so it doesn't use power anymore. Now imagine you have a board which has like lots of outputs for diff power on there. This is an early prototype. It'll be different. It probably also won't be 8 ports anymore, but like 6 ports or whatever. Now you can change those individually, and if those are certain downlights or certain LED strips or whatever in your house, it would be nice to be able to control the power to those individually. So now you can make a segment in WLED for each output, and then if your home automation or your home assistant or whatever turns off a certain output, it can do that individually, and then also individually turn the power off to that remote board, saving power and being safer, etc., etc. So that's kind of where this feature is leading to. If you have a board with lots of outputs on there, you can now switch those individually instead of everything having to stay online until all of them are off and then the power gets switched off. No. We can now do that individually per port. Saves power, saves electronics, saves heat, etc., etc. Yeah, so that's the idea. I can understand no one watching is following where I'm going with this. It'll all become clear in the future, okay? Yeah. He had a wild deer wandering around. Your 7.5 kilogram cat was stalking it. What? Okay. Yeah, so I've been wanting this feature for a while, but I can't program for shit. And it's fairly simple. So Fable came back, you know, the AI they pulled away after I used it on stream last time. They were like, whoa, what is he doing? What is he doing with our AI? He's designing PCBs with our AI. The US government shut it down immediately after the stream. They were like, no, we can't have this. This is way too powerful. We can't give that to common PCB designers in the Netherlands. It's only for US citizens. So they disabled Claude for everyone, or sorry, the Fable for everyone. But now, 2-3 weeks later, they've come to they've relaxed a little bit, and probably Anthropic paid them like 100 million, and they're like, oh, thank you for the donation. Yeah, now your AI looks a lot better. Thank you. Yes, very good. So I once Fable came back, I used it to like, hey, could you make these changes for me? And it took like 10 or 15 iterations, but right now it's working great. So yeah. The functionality is, yes, and the diff power system also, yes. That is how I'd like it to work. And in my opinion, that doesn't exist yet, or at least not for the price point I'd like it to be. So I'll make it myself. That's kind of what's happening with all these things. But, yeah. That's also what we worked on with the wall panel sensor project. Same thing. I don't want a $500 wall sensor if I can build it for $100. So we're building it. So yeah, that is the idea. So some more progress, more about this in the future. Diff power, the first wave, as I call it, should be getting close, much closer. And yeah, Queen Software Division. No, we'll see where it goes, but. I know a lot of projects hate AI submitted code, so I'll talk to them and see how they want to proceed. And yeah, we'll see. So, everyone, thank you for watching. I am sweating because well, the doors are now closed, so it's 29 degrees here in the garage, which is an excellent temperature to leave the room. Oh, okay. Yeah, you could probably do stuff like that too. Anyway, thank you for watching, and I hope to see you guys back next time. Bye-bye.